Thank you very much for that introduction. My name's Alwyn Elliott. I'm a PhD student at Imperial College, and together with the University of California, Berkeley, we've been looking at how you can improve the integration and lifetime of piezoelectric energy harvesters. So the objectives of this work was first of all to maximise the power you can generate from a piezo, but also how you can deal with the issue of piezos degrading over time, especially when you actuate them. The techniques we used to do this was, first of all, single supply pre-biasing, which some of you may have heard of before at IEEE Sensors last year, but also then this new technique or operational mode called force return to zero, which hopefully I'll demonstrate to you that it gives us some great benefits. So I'm sure you've been walking around the last few days and you've seen there's been plenty of applications for biomedical sensors, but one of the biggest issues they've come across is the lack of power and the problems with batteries in that sense. And so I hope that energy harvesters can eliminate this constraint. However, when we consider that most energy harvesters are essentially an actuator in reverse, and these actuators are normally stated to do 500 million cycles, and if we just run that at, say, a 50 hertz mechanical excitation, in less than a third of the year, your actuator has actually exceeded its lifetime. And if that's your power source, your pacemaker, that's not great news. So what we want to do is look at how we can modify power extraction techniques to improve this. So first of all, let's consider an energy harvester as a mass spring damper system. I'm sure you've seen it before. But specifically with piezos, we find that the output capacitance is in shunt connection. Now what this means is it's difficult to achieve an optimal damping force to extract the most amount of power. And we end up with what's known as a weakly damped, velocity damped resonant generator, as shown here. So, which is difficult to control in the sense that if we shake it harder, we can't increase the damping force. However, if we use charge modification techniques, we can modify its behavior so it actually becomes what's known as a Coulomb damped resonant generator with very controllable dampening. And we can simply set the optimal damping force using the equation shown here. The equation here tells us the optimal force we need to apply in terms of the voltage. So how can we do this? Well, the single supply pre-biasing circuit operates by placing charge onto the piezoelectric material itself, and this generates a Coulomb force which opposes the motion of the beam. If we oppose the motion, obviously we increase the work done, more power generated. So how do we implement it? Well, it's quite simple. We can take a piezo circuit, a piezo harvester, which is this current source and capacitor in parallel, connect it to an inductor and place it in the standard H-bridge circuit in power electronics. We first of all assume that the beam is initially its maximum deflected position, and there's no charge on the beam. Then we can close switches S1 and S4 and allow current to flow through. We can place a charge on the beam. Weakening those switches and allowing the beam to bend to its opposite position increases the charge on the beam itself and increases the voltage. Similarly, we now close switches S1 and S4 again. This now discharges the energy back off the piezo into the supply, and that's how we realize a net energy gain. Even those switches, closes the opposite pair of switches, which applies the pre-bias with the opposite polarity, and hence the Coulomb force is now acting in the downward direction, and so the system repeats. So using this technique, with the maximum power we can generate is given by the equation shown here. And as you can see, it's the open circuit voltage, VPO, squared, times by the frequency of the mechanical excitation applied, times by the capacitance of the actual piezo itself, multiplied by this gamma over 1 minus gamma squared term, where gamma is the fraction of voltage that's conserved on the capacitor when you discharge it. So when you resonantly discharge it, the amount of voltage charge that's left on it is determined by this coefficient. So now let's look at how piezo harvesters actually degrade. Well, some work done by Marcus Kane and his friends in 1999 looked at how mechanical loading and cyclic loading on piezo harvesters were affected. So we see with mechanical loading over the cycles, the D33 property really decreases. And this is the one that determines, it's the piezoelectric coefficient, determines how much power you can get out of it. Now we can alleviate this to some extent by applying a higher pre-bias voltage. However, there's another issue. When you're electrically cycling it, so when you're continuously actuating up and down, there's a voltage going across it. There's also electrical cycling occurs, and this tan delta term here is the lost tangent. So the more we electrically cycle it, there's this increase in resistance, and we end up with the loss tangent increasing. Now, as a result, as we increase the loss tangent, we end up with the gamma term decreasing. So there's less charge. There's more charge being left on the capacitance on discharge. So we end up with this BREM term. So there's this voltage left on here. Now, the problem with this is when we now pre-bias it in the opposite direction, we have to overcome this voltage first, and that's where we get a loss in power as it deteriorates. And as you can see from the equations here, we're looking at the single supply pre-biasing circuit at a very new, sorry, this should say increase in loss tangent here, at a very high inversion factors. That's a brand new piece of piezo. It's brand new. It's very good. We perform very well. But as the piezo degrades and this voltage inversion factor falls, or the loss tangent increases, we find that the power generated really falls away. And another technique, which I'm sure some of you heard of, called synchronous switched harvester inductor, then performs better. So what we want to do is find a way of not only achieving these high power generation techniques, brand new piezo, but also, achieving a low inversion factor, so as the piezo degrades. So the technique we developed was called forced return to zero. And what this was a modification of the original SSPB circuit. And so the idea being that if we can just short the piezo out itself, we can remove this excess charge, we don't have to overcome this extra energy requirement. And the simple way of doing this is moving the inductor from the center of the H-bridge circuit up to the top of the high-side switches. And it's quite simply clear we can either short out S1 or S2 or S3 or S4 in the center of the process and remove this excess charge. So how does this now compare to our original techniques? Well, the line in red now shows our forced to return to zero case. So the voltage inversion factor when it's brand new is great. We got a large amount of power being generated. And as it deteriorates more slowly than the original case, and then performs much more like the SSHI circuit. And therefore you can see that this is like a best of both worlds. So we've seen that the theory says it. We then want to try and verify it using PSpice. And to simulate a degraded piezo, we simply added a resistor in series with the piezo. And then we swept the voltage across whilst measuring the power generated. And what you can see from here in this red curve is the forced return to zero case, where clearly there's a higher peak power achieved at a higher voltage. But also you can see that it's less sensitive to this VCC voltage, which when you consider that that if the energy harvester's mechanical excitation were to vary, then we also need to reconfigure what voltage we need to apply here. So this decreased the sensitivity. So we've actually got an unexpected bonus here. And it's about 10% power improvement you can see in terms of peak. So then we looked at implement this practically. And we took our circuit we presented last year, IEEE sensors, and we thought, it's just simply a case, move the inductor to the top here, and it should all be hunky-dory. However, what we realized was that when you place an inductor at the top here, when you place an inductor at the top here, actually affects our gate drive circuits, because it removed how they were being referenced, so our circuit didn't actually work at all. Instead, what we realized is we placed two inductors that are the same value in the low side, we can still short out the high side. However, this isn't a brilliant solution, but it is a solution, because obviously you're increasing the amount of space you're having to give up towards the inductors. But when we looked at the actual curves here, you can still see there's definitely an increased peak with a forced return to zero case compared to the original case. So in conclusion, piezoelectric energy harvesters are known to degrade with mechanical excitation. There's nothing we can do about that really. However, the loss tangent increases as a result, and the coupling coefficient decreases. This generates a reduction in power generation. However, we can modify what's known as the SSPB circuit to extend the usable lifetime of the energy harvester. And future work I believe we need to do is to modify the gate drive circuits used so we can remove that use for a second inductor. Finally, I'd like to say a quick thanks to both my colleagues at Imperial College and also Berkeley University, and also ABB for sponsoring the work. And if you want to know anything more about this, please join us in PowerMem 2013 in London this December. Sorry, I'm part of the coach. I'm on the local organising committee, so I've been asked to do this. Thank you very much for listening.